at Georgia Tech. She does work on AI, neuroscience, language. It's exactly the type of speakers we'd love to have at the city. And there was some controversy about whether or not language and thought are separate, and I guess you're going to end the controversy.
So with the rise of large language models, one thing that we have observed is a proliferation of studies that one might call AI psychology, where researchers take cognitive tests, often initially designed for humans, and then apply them to AI systems with the goal of figuring out their underlying capabilities. And it's a really popular thing to do these days. This is a bunch of papers from last year cognitive science conference, which all have words like LLM in the title. And the interesting thing about them is that they use LLMs as models, not necessarily of language, but all kinds of stuff, right? So these are papers looking at personal values, creativity, episodic memory, analogical reasoning. So we're seeing that now we are using large language models not just as models of language, but as models of all other kinds of cognitive capacities, or potential models at least. And even though this avalanche of studies is really noticeable now that it's really easy to do this, right? You can just go and ask ChatGPT questions and measure its responses and then publish a paper about it. The studies aren't new, but the idea is old. The idea really goes all the way back to the Turing test, where the setup is pretty much the same. You have a human observer interacting with either a computer or a person, and then the goal is to figure out the underlying cognitive capabilities of your interlocutor through a chat interface, right? Like what you would have with ChatGPT. So the idea behind the Turing test and a lot of those cognitive tests is to use language as a window into thought. And it makes lots of sense, as I've just told us. Language is a really powerful tool for communicating ideas between two different minds, two different entities. And so if you want to figure out what's going on in somebody else's head, oftentimes the easiest thing is just to ask them. So this relationship between language and cognition is something that we observe all the time in the real world, but as a result, it is often possible to start conflating the two, right? So they go together, and so you kind of, humans might tend to mixing them up a little bit. So the one error is mistaking fluent language for fluent thought. We can formalize it as a logical fallacy, observing someone or something, being good at language, and then kind of jump into the conclusion that they must be good at thinking as well. A common example is something that you might see with humans, where you might have a speaker who is very eloquent, very persuasive, very charismatic, and you tend to kind of buy in what they're saying, even if the content of the speech might be kind of vacuous. On the flip side, you might observe someone or something being bad at some kind of thinking and then jump to the conclusion that they must be bad at language too. And we've been seeing that with evaluations of language models, especially when they first came out. People would kind of point out a specific flaw of reasoning in a language model and dismiss it altogether without acknowledging all the impressive advances on the language side of things. And so really the main point that I want to make is, when evaluating LLM capabilities, we really should try to dissociate language and cognition, intelligence, thought, however you want to call this host of cognitive capabilities. And so in the talk today, I am going to, first of all, propose a framework that can help us dissociate language and cognition, and that's the notion of formal and functional linguistic competence. I will then delve into a particular domain where I have a particular interest, and that's the notion of generalized world knowledge, which happens to be a domain where it's actually kind of hard to disentangle language and thought. And then briefly conclude about moving forward in the relationship between neuroscience and cognitive science and AI. So This first chunk of the talk is based on the paper that we wrote along with Kyle Mahowald, Ev, and other lovely co-authors. And it's really inspired and based on all of the neuroscience work that Ev has done on language in the brain that she told you in the previous talk. So just to briefly summarize, is that in the brain, we know that language and cognition are dissociable. Language processing takes place in its own separate network. This network responds to language at different grains, words, phrases, and sentences. It responds during listening and reading, so different forms of language comprehension, speaking and writing, so different forms of language production. And it responds to all different kinds of languages a person might know. And not only does this network respond to all different kinds of language, it's also selective for language versus other things. So fMRI evidence, this is a schematic from Ev. You see a response in the language areas being high to all kinds of language comprehension production paradigms. But for other tasks like math and logical reasoning and problem solving and others, you actually see pretty low responses as recorded with brain imaging. And then there is complementary evidence from patients, which I've also mentioned, where you have patients with really large lesions causing severe issues with language comprehension and production, and yet a lot of the cognitive capabilities might remain intact as long as the lesion primarily targets language areas and not other areas in the brain. So we see this dissociation between the specialization for language in particular parts of the brain. But now let's move one step beyond that. So even though we have this network that is responsible for core language knowledge, it has also shown that it's sensitive to all kinds of syntactic manipulations and lexical semantic manipulations, this network doesn't operate in isolation. Right? The goal of language, as we've said, is to deliver a message from one person to the other. So if the language network is processing some kind of information that you're receiving, it doesn't stay there. Instead, it would go to other parts of the brain that would then make use of that information. For example, the language network works closely with a set of regions responsible for social knowledge and social reasoning, for the default network that is responsible for situation modeling and tracking information across the span of a narrative. Many different regions that Shaylee mentioned that activate in response to different kinds of world knowledge and different kinds of conceptual information. The multiple domain network that's responsible for general cognitive tasks such as logical reasoning or math. And we have preliminary evidence for a set of brain regions that might be responsive to semantic tasks, whether linguistic or not. And so what happens in real-life language use is that the language network constantly communicates with all these other areas in the brain in order to deliver information back and forth for the agent to accomplish the communicative goals in the world. And so we can take this picture from human cognitive neuroscience, and then we can start asking questions. What are these capabilities? What computations underlie every one of them? How is this information transmitted? And we can ask these questions both for human brains, but also for artificial AI systems. So now we have a taxonomy, a classification of the kinds of capacities we would expect an artificial intelligence system to have. And so what we can do, we can group them into two classes. One is formal linguistic competence. So these are language-specific computations that in humans are carried out by the language network. And on the other hand, we have functional linguistic competence. These are non-language specific capabilities, right? So you can apply your social reasoning to just visual events that you observe in the world. You can solve a math problem using not a word problem, but just a symbolic math problem. So these are not language specific, and yet they're essential. They're essential for you to actually be able to use language successfully in the world, and they would be essential for an AI agent that wants to communicate with a human effectively. So just to give you a concrete example, an example of formal competence, is the keys to the cabinet are on the table, knowing that the verb here are should be plural to match the keys and not singular to match the cabinet is an example of knowing the rules of English grammar, and so that's an example of formal competence. And formal competence really became kind of easy for language models starting with GPT-2 and definitely with GPT-3. And it's really a remarkable scientific and engineering breakthrough. We had multiple speakers earlier in this workshop tell us how that is something that people in NLP have been trying to do for a really long time, and now we can. And what they also told you is that it's not something that linguists were necessarily expecting, right? So it goes against the intuitions of many people about how language might work and what is in principle, in theory, even learnable from linguistic input, right? So it's a really remarkable model of language and formal linguistic competence. On the functional side, we might have a problem like that. 6 birds were sitting on a tree, 3 flew away, but then 1 came back. There are now 4 birds. Knowing that the correct answer here is 4, if you're predicting 1 word at a time, you need to predict the word for, so the lexical form, but you also need to do some basic math in order to predict which number you're supposed to plug in here. And so that's an example of functional competence, and here specifically just arithmetic. And so that's something that actually starts to become challenging for language models. We've seen successes, but GPT-2 certainly cannot do that, right? And even now, if you give this specific problem to language models, they'll be just fine. But if you start adding additional steps or making numbers much larger or mathematical operations more complicated, that's where you start seeing some breakdowns in their capabilities. Even when they do succeed, there are questions that arise about how they do it. So we've seen that even when models succeed on, say, theory of mind tasks, it seems that often their performance might rely on memorization or heuristics and doesn't generalize to problems that are very different from what they've seen in their training or fine-tuning data. And an interesting shift that we've seen is that people have actually been shifted away from pure next word prediction to fine-tuning these models on specific tasks or adding additional modules. So really, I would say that with ChatGPT, we've seen the end of pure scaling via pre-training, and then there's a lot of work that's ongoing to try to augment the capabilities of these models, either by fine-tuning them on these tasks or by pairing them with a Python execution shell or with a database like in RAG, right? So these are all examples of augmenting the pre-trained capabilities of language models to enhance their functional competence, right? So the formal competence, something that you can acquire by raw pre-training. Functional competence is something where we see that it's not so easy, you need to do additional things. And so, looking at this capability, what we really want from an artificial system is a system that looks something like the human brain, where you have language processing, maybe a language processing module, that then interacts with all of these other systems that are specialized for other kinds of capabilities, right? So that will be a human-like system of language use. And just to demonstrate you, so we can take a simple example. This is the language network. This is the multiple demand network that F has introduced. That's the network that responds to diverse, challenging cognitive tasks. The harder the task, the harder you need to think, and the more activity we see in this multiple demand network. And so for a problem like the bird problem, you read it, it flows into your language network. The language network extracts the meaning of these words here, but it cannot do math. And so instead, it might pass the relevant information to the multiple demand network. The multiple demand network performs the relevant computation and returns the answer, in this case 4, which then you can verbalize, again, using the language system. Right? So we think that the processing of a problem like that is fairly modularized, at least for capabilities like logic and math. And so then you can ask, okay, but we don't think that's how models today are organized, so what does that mean, right? Can we make them more human-like? Do we want to? And so there are a few different options that we point out for how we might arrive at a system like that. One option is what we call architectural modularity. So you build in different modules and then stitch them together, right? You're like, I want a language module, I want a math reasoning module, I want a social module. I'll build it in, I'll maybe train them separately, and then I'll put them together. So it makes a lot of sense. It maybe is the easiest to engineer, but we know that it doesn't always work. From past attempts in AI, we know that the systems can be fairly brittle. But for vision language models, that's kind of what you have to do. You have separate components for vision and language, and then you put them together. Another option, though, is you can say, well, okay, I don't trust myself on knowing exactly what the relevant components are, but maybe I can predispose my system to become modularized over the course of training. And so you might try to set it up such that training is end-to-end, but maybe your training data is curated in a particular way, or you have multiple objective functions such that you end up with different modules. And importantly, the architecture of the model would need to allow you to have those different submodules, which the current transform architecture doesn't necessarily. And then I have here the mixture of experts like addendum. So I think mixture of experts is kind of an example of different, subcomponents that become specialized without you telling them in advance what to do, except that we're talking really about the macro level structure, whereas the mixture of experts are little experts, so you kind of diverge and merge all the time, right? Whereas you might need some of the kind of longer stretches of time when an expert needs to do its job before they all come back together. And then one possibility that I want to acknowledge that also came up in Ev's Q&A is that, well, maybe some of the models today already show this kind of structure and we're just not seeing it, right? So I think it's an important thing that we have to acknowledge. I would argue that they don't have this because their behavior is not human-like, and so we can kind of predict that they don't have quite all the same parts in place that you would want them to. But it is definitely possible that some kind of specialization is already there. We just haven't been able to find it with existing interpretability methods. Okay, so this is the end of the first part of the talk. So if there are any questions, I can take them now before maybe moving to world knowledge. Yeah.
The reason why most people are interested in large language models, excepting for linguists, right, is the functional competence of these models. And it's totally, I think, right to point to all the ways that modern large language models have been augmented, right, beyond just distribution learning. But for text models, that augmentation is happening through language, right? So you're fine-tuning them largely on language. I mean, there's some math stuff and programming language. It's unclear how much that impacts things beyond programming and math. And so is that an important data point for you? Is that relevant, that all of this functional knowledge in LLMs is coming from language?
Yeah, and I think actually the next portion of the talk will maybe try to kind of address that more directly. The idea is that language contains all kinds of signal about the world, and so when you pick up on the statistical structure, you end up picking up on a lot of stuff about the world. I would argue that doesn't necessarily give you coherent world models, right? If you are a pattern matcher, there might be certain things that pattern matching won't give you that will impair your ability to do algorithmic reasoning step by step with an arbitrary number of steps. Chain of thought seems to help, which is cool, but right, that's something where we've seen the need to augment. Or for theory of mind, you need a coherent mental model of the world and how the world looks like through the eyes of another person. And so it's not just about what kind of patterns there are in the data, it's also about the internal representations that the model needs to learn to successfully use that knowledge, right? But yeah, I think, you're absolutely right. right? It's interesting, like a lot of the talks we've had this week were about formal competence, which is very important and again overlooked, but out there in the world, people don't care about a big NLP advance that now we have a model that can produce grammatical English. They care about a model that can think, right? So I think that's absolutely true. Okay, so to me at least, in certain cases, the distinction between formal and functional competence is kind of easy to see. You know, when you are seeing a math problem about birds on a tree, you kind of understand that the task of extracting meaning from this problem written in English and the task of doing the math, like these are two separate things, right? I think it's pretty intuitive. But there are other domains of functional competence where the line between language and thinking becomes kind of blurred. And world knowledge, I think, is one of such domains. And so we're going to talk about why I think it's complicated to separate out language and thought and world knowledge, and then talk about 3 different case studies or projects that I have in this domain, and these are all LLMs, so there's going to be no neuroscience from this point onward. Okay, so as we just said, language contains a lot of information about the world. So lots of information is just factual, right? So Paris is the capital of France is something that you can learn simply by memorizing strings of words that you see in the training data. But other kinds of information is more subtle, so you can observe the distributional patterns in the data. So here, for example, you might see possible colors of the sky and then construct an internal distribution about what kinds of colors a sky might take, which are more common, which are less common. And so it's this implicit distributional information that we're going to be focusing on today. And so it turns out that distributional information from language is very rich and aligns quite well with information from other domains like vision. So in this example, you have co-occurrences that you can extract, in this case for animals, from different sentences in the text. So, you know, if the 2 animals are in the same paragraph or in the same document, they are represented as more similar. And then similarly here in photographs, if 2 animals appear together in the same photo, their similarity increases. So you can construct the similarity matrix projected into a 2D space, and it turns out that the representational spaces for language and for vision are quite similar. And then, you know, this kind of work has been followed up in more recent language models and vision models as well. And then similarly, in the domain of color, if you take the perceptual color space and similarity of color embedding words, you see a good degree of alignment. So red and orange are represented as more similar than red and blue. And this aligns very nicely with Surya Ganguly's work that he mentioned on Monday about being able to take a language space and a vision space and just rotate them to align them, right? So it's all the same kind of evidence here. There's one problem, that the information from language is biased. So when I came up on stage today, I didn't just say, oh, you know, this morning the alarm rang, I woke up, I brushed my teeth, I got dressed. Like, you know, I'm talking to you about information that doesn't faithfully describe my experience. I'm talking to you about information that's relevant and important and interesting in some way. So this phenomenon is known as reporter bias. It was described in human-generated text, and Yerin Choi, for example, showed that that language models are susceptible to reporter bias, that they indeed overrepresent rare events in the world. And I, you know, just have this like really fun, nice example. So if I Google square wheels versus round wheels, I actually get more search results for square wheels relative to round wheels. And the reason why is, well, why would you want to specify that the wheels are round? That's kind of the default. So here you would choose to talk about stuff that is unusual, so when the shape is square. So a lot of this basic information that's kind of implied would be underrepresented in human text. And then one other reason why, you know, it might be useful to separate out language and world knowledge is the kind of work coming from Shaley and Alex Huth and this kind of whole brain encoding model style work is that they show that, look, these are responses to a narrative, the linguistic narrative. They go way beyond the language network. And specifically in regions outside the language network, you see parts of the brain responsible for specific meanings lighting up in response to certain words. So social regions of the brain would respond to words like love and relationship and stuff like that. Right? So we see that in the brain, certainly we have this kind of dissociation between language and world knowledge. And so it kind of gives us pause for equating the two. Okay, so now let's look specifically at what it is that language models can and cannot learn from language. And so we're going to start with this phenomenon that or area that in cognitive science is known as generalized event knowledge. Generalized event knowledge refers to our capacity to store templates of common events observed in the world, right? So we know that the fox chased the rabbit is a perfectly plausible event, whereas the rabbit chased the fox is a little bit weird. It's not impossible, but it's implausible. And then the fox chased the planet is something really, really bizarre and really weird altogether, right? So very basic common events that can be described with just a few words. We see, humans are known to make really rapid inferences about the plausibility of events like that. And so we asked, does generalized event knowledge naturally arise in pre-trained language models? Can they pick that up simply by being trained on next word prediction? So this is a project that we did with my colleague Karina Kauf. And so we used here a minimal pair paradigm. So we had sentences like the fox chased the rabbit versus the rabbit chased the fox. So we're switching the agent and the patient to manipulate the plausibility. We feed them to a language model to get a log probability score, so how likely the sentence is under the model. And then we compare the two. If the score for the plausible sentence is higher than the score for the implausible sentence, we give the model an accuracy of 1, otherwise 0, and then just average across a bunch of sentence pairs. And specifically, we looked at two different kinds of sentences. So these are animate-inanimate interactions. So the teacher bought the laptop versus the laptop bought the teacher. And in this case, the laptop bought the teacher is an impossible event. Like, by default, it's not something that can happen. You can kind of make up a story, but generally, it's like really weird. And so here we see that humans in red perform perfectly. And models, these are models from a few years back, they perform pretty much as well as humans. And here we have a bunch of language baselines, which are very basic language models, not LLMs, and even they perform above chance, suggesting that the signal is really, easy to detect in language corpora, in language inputs. We also had animate-animate events, like the fox chased the rabbit versus the rabbit chased the fox. The rabbit chased the fox is not impossible, but it's simply unlikely. And here we saw that there is actually a performance drop. So models actually underperform relative to humans. So these are large language models. They're above chance, but not as good. And then these baseline language models are actually pretty much at chance. So it's much harder to judge plausibility in this particular case. So we see a gap between how well LLMs perform on animate-inanimate sentences versus animate-animate sentences, and so we call that in the paper the gap between the impossible and the unlikely. Yeah?
How accuracy is calculated?
So we're comparing pairwise log probabilities for pairs of sentences like that. If the log probability for the plausible sentence is higher, then accuracy is 1. If not, it's 0.
Thanks.
And so there might be many reasons for this gap that we observe here. And we can talk about reporter bias again, implausible events being overrepresented. Or we could maybe consider going all the way back to the formal functional competence and frame it in this way. Here, the laptop bought the teacher actually violates a linguistic property known as selectional restrictions. So bought here requires an animate subject, right? So someone animate needs to be doing the buying. And so as soon as you see the laptop bought, there is a violation there because laptop is inanimate. And so maybe that's actually a domain of formal competence. You might expect that to be a linguistic computation. Whereas here, the rabbit chased the fox, there is nothing linguistically wrong with the sentence, so it's a violation of our graded event knowledge. And so you might expect that to be maybe in the domain of functional linguistic competence. And so this gives us a prediction to potentially go back and see whether the brain signatures for these two kinds of events actually differ. Haven't done that yet, but that would be one way to try to separate out formal and functional competence in this case. Yeah?
You can have also something that's inanimate. You say work has wasted his soul. That's perfectly...
Yeah, so it depends on the verb. So certain verbs might be more amenable to inanimate subjects than others. Yeah, so selection restrictions, you would expect them to be verb specific. We also looked at how the log probability scores generalize across different versions of sentences that we had. So you can have an active and a passive version of the same sentence. The author finished the novel versus the novel was finished by the author. So that's an example of syntactic generalization. And for humans, you see a 0.96 correlation in the plausibility scores between these two versions, right? That doesn't matter. The meaning, the plausibility is still the same. And then actually for models, you see pretty high correlation scores as well. So models as early as GPT-2 and BERT, they actually have learned to abstract away from the active-passive, from the surface level form of the sentence here. So they can generalize across syntactic forms. We also looked at semantic generalization. The author finished the novel versus the writer completed the book. So these are synonymous sentences. Every word is different, but the meaning overall is similar. And so humans indeed show a 0.9 correlation for these sentences. And the models actually show a much lower correlation. It's still positive, it's still significant, but we actually see that they struggle a little bit more with semantic generalization relative to syntax, right? So highlighting another potential formal functional competence distinction. Right, so you can do all kinds of things. That's like something I love to do with these kinds of minimal pair situations or any kind of controlled experiments. You can then do a lot of follow-ups to figure out what exactly is going on, what exactly a model is doing and not doing. So, you know, as an experimentalist, it's something that I think is really, really fun. Okay, and then the last thing on this project is that we, asked, okay, these are log probabilities, these are Bayes models. Now we have prompting, and so we had the reviewer being like, oh, I just went and asked ChatGPT, is the sentence plausible or not? So we said, okay, what happens if we take newer models that can, respond to prompts, and what is the relationship between the log probabilities and prompting? And what happens when the models are instruction tuned? Does this knowledge get better? Does it get erased because they get instruction tuned on other things? What's going on with common event knowledge? So these are our results. We looked at Mistral, Falcon, and MPT, Bayes and Instruct version, about medium-sized for these models. What we found, first of all, is that the impossible unlikely gap remains. So we replicate this result even with newer models. Log probabilities are consistent across models, whereas prompting is hit or miss. So log probabilities, we see the same pattern across all models, doesn't matter what exactly you do, whereas prompting, it works for one model and totally fails for another. You can do prompt engineering, you can tune, but you can kind of see that it's much harder to get that knowledge out of a model. So log probs, in a way, provide you a more direct access to the internal knowledge of a model. And then conclusions from Bayes models actually hold for instruction-tuned models. We didn't see erasure of common knowledge. We didn't see augmentation. We actually saw that they perform pretty much the same way, at least in this sample here. And this difference between log probs and prompting is something that will come up in the rest of the talk as well. And of course, it goes all the way back to Jen Hu and Mike Frank's work on task demand in large language models. And I'll talk about that more later. Okay, so the takeaway from this whole line of work is that LLMs systematically distinguish possible and impossible events, but are less consistent with likely versus unlikely events. Yeah. One problem with our paradigm is that we use single sentences. So one way in which a model could do Inference is just, has it seen strings like the fox chased the rabbit versus the rabbit chased the fox? So in principle, it could do well simply by memorizing its input. And so in this next project, we wanted to, A, get rid of the dependency, try to control for memorization of just pure sentence sequences, and B, broaden our range to test the whole range of domains that we know are important for humans, and try to do it in a way that is fairly systematic and extendable and generalizable. So we call this project Elements of World Knowledge, or EWOK, and it's co-led by me, Alok Sath, and Ben Lipkin. And the team is pretty large, and it includes a bunch of cognitive scientists working on all these different domains of knowledge. So the goal was to take a bunch of domains of knowledge from cognitive science, right? So Fei Shu talked about a lot of them in the talk yesterday, and so developmental psychology is definitely a big source of inspiration for what are the core concepts, the fundamental concepts that humans use when processing the world around us. And so let's just narrow in on one example. Let's say we take the domain of social relations. We're gonna take some concepts from that domain and test them by juxtaposing them using templates. So let's take the concept of a teacher. We can maybe juxtapose that with the concept of a student. You don't have to have two concepts, but a lot of the time it's kind of the easiest way to do that. And then we write a template, like we have context sentences and target sentences, and each of them is a minimal pair. So in the context, we have agent 1 assigns homework to agent 2 versus agent 1 submits homework to agent 2. And then the target is agent 1 is agent 2's teacher versus agent 1 is agent 2's student. And then you see those agent thingies, they are placeholders, because now we can generate multiple items from that single template in a very controlled way, of course. And so we can have combinations of context and targets. So Fatima assigns homework to Jose. Fatima is Jose's teacher. Makes sense. Fatima assigns homework to Jose. Fatima is Jose's student. Kind of weird. So you see that context 1 goes with target 1, but not target 2. And then context 2 goes with target 2, but not target 1. Right? So it's a minimal pair of pairs design that tests our knowledge of the concepts. And so we tested a bunch of different open models from Hugging Face. We compare them with Word-to-Vec baseline versus human performance. And so this is one domain. This is the easiest domain. And these are social interactions, so concepts like help, hinder. And humans are perfect. Models are pretty good. Nobody is as good as humans, but some get pretty close. Those little dots here, these are different versions of the same data set. So whether you use Fatima and Jose or Tom and Ben, right? So you see here that actually the specific variables, when you fill them in, like names, they actually affect model performance, which, they shouldn't ideally. The hardest domain is spatial relations. So we see that humans here are not quite at ceiling, but pretty good. There are funny, interesting reasons why they're not at ceiling, which I can talk about. And models we can see are pretty bad. So some of them are above chance, but there is a substantial performance gap here. And so what we can do is then we can look at all of these domains, arrange them from best to worst. And so one thing we can notice is that social interactions and social properties are easiest, at least in the set, and physical relations and spatial relations are harder. So we see this dichotomy where social information seems to be easier to pull out from text than information about the physical world and relational information in particular. Right? So these are the kinds of insights that we can get by looking systematically across different domains of knowledge and evaluating large language models. And then so these results I'm showing you here, they were done with log probabilities of a target sentence given context 1 or context 2. But of course, you can also do prompting, and here we also show that prompting doesn't work as well, at least in these models that are not super large, although we do get all the way back up to like 30 billion and 70 billion for llama. So, once you get to 70 billion, then you're like, okay, one of the two prompting techniques we used matches log probabilities, but doesn't even go above, right? So log probabilities remain a reliable source of signal, especially for those smaller models that get overwhelmed by the task demands of prompting. Yeah?
Do you think social interaction and physical thing can reflect the reporting bias in the training data of the models. For example, it might be more likely for a person to talk about social interactions with other people and then just talk about like physical situations or physical information.
Yeah, absolutely. I think that the difference between the social and the physical domains is a reflection of the reporting bias. The example of the square wheels versus the round wheels is an example of that. It's physical information about shape that people can get through vision, so maybe they don't need to talk about it as much, whereas social information is abstract, so you might actually use language to exchange that information because you don't just get it from vision as easily. Yeah.
Would you expect that by testing a visual language model, in that visual language model, to see better performance in like spatial tasks?
Maybe, right? So relational knowledge is still not good in these models, right? If you say to put like a banana on top of a box or a box on top of a banana, they're not very good. So given that our worst domains are relational, then maybe not actually. But it is a good, question. I think vision language models shouldn't be conflated with language models. Vision language models are not as good at formal competence. Syntactic knowledge seems to be weaker in them than in pure language models. So it does change the game when you add visual input, but specifically for spatial and relational information, maybe not. Okay, and then since Alex Worth talked about BabyLM earlier this week, EWOK was actually a test-only benchmark in the latest iteration of BabyLM. Maybe the reason why it didn't come up in Alex's talk is because models didn't do well on EWOK, right? So models that did well on BLIMP, which is a grammatical benchmark of formal competence, they still aren't doing well on EWOK. There's kind of a correlation, like if you do better on BLIMP, then maybe you are a little bit above chance on EWOK. But this is really further evidence that functional competence here, world knowledge is harder than formal competence, that learning grammar is easier than learning detailed, in this case, context-sensitive information about the world. So I actually think it's a useful data point, even though it wasn't particularly useful for discriminating the models in this version of the competition. Yeah. So the takeaway from this work is that basic world knowledge in large language models varies drastically by domain, with social knowledge being more salient, easily available to models than physical and spatial knowledge. And EWOK is not meant to be just a single data set, it's a framework. So A, you can generate new examples with templates. B, you can add new concepts, you can add new domains of knowledge. One domain that's up for grabs is temporal relations, like before and after and during, right? We just didn't, get to add this domain, but it's very much there, and there are many others, right? So it's meant to be extendable and generalizable, and so this was EWOK version 1.0, and so, definitely feel free to talk to me if you're interested in building upon this framework. And then for this last project, this is actually work that is very new. We just submitted it, so you're gonna witness me trying to explain it for the first time. As I mentioned, task demands is something that I think has been a really important observation by Jen and Mike, where in order to answer a prompt-based question, you need to interpret the question, you then need to access your internal knowledge that you need, and then you need to format it in a way that the prompt expects you to format it in, right? So even like multiple choice, you need to interpret what A, B, C, D is, and then map your knowledge back into A. Like, it's a lot of work. It's very hard, and it's something we don't really appreciate always. And so here, within that kind of general paradigm, we thought about one particular task demand that we know matters for humans, and that's the yes bias or the acquiescence bias. So we know that little children or even adults in surveys with kind of ambiguous preference questions, they tend to answer yes to questions, right? So for example, you have like a toddler and then you show them a book and you're like, is this for reading? They're like, yeah. Is this round? They're like, yeah, even though, it's not round. So there is a tendency to say yes more than you should. And, usually the reasons why we think people say that this bias exists is like social reasons, you want to conform, you don't want to disagree. So these are very kind of high-level cognitive explanations. And so we wanted to look at yes bias in large language models with my master's student, and we asked, well, does yes bias arise in large language models as a result of statistical learning on language inputs and/or instruction tuning? Right? Is that something that you can just kind of pull out from the input? Maybe in the input, people just like say much more yes to questions than no, and then it's kind of a pattern that large language models pick up on. And then the next question is, well, okay, if this bias exists, then does it mask existing model knowledge? Is it a problem for us, right? So then, can we try to correct for this bias, and will that improve model performance? Right, so it's a very particular kind of the relationship between the task and your internal knowledge. So maybe by saying yes too much, they're actually hiding that they know more than they do. And so here, we took, in this case, EWOK. We adapted it into yes-no questions, right? So is Fatima Jose's student, right? It was very easy. And we tested a bunch of models, different sizes, 4 different families based on instruct or chat. And we looked at the relationship between their bias and their accuracy. So a bias of 0 means that they respond equally to yes and no. And in our data set, the number of yes and no questions was matched. So that was the correct behavior, to have an equal number of yes-no responses. And then negative scores means that they are biased toward no. Positive scores means that they are biased toward yes. And so we saw the following pattern. We saw, first of all, that the models are biased. So very few models stay on the vertical line, as they should. But we saw that this bias is not a uniform yes bias. In fact, a lot of models are no biased here. And specifically, the bias seems to vary with model family. So the MPT models are all over here. The Falcon models are all kind of over here. So we see that there is bias, but it's not uniformly a yes bias, and it varies a lot depending on the model family. This was a first example, and so here we're testing 0 shot. So 0 shot means you just ask a question, right? You're saying, Fatima assigns homework to Jose, it's Fatima Jose's teacher. We also had a few shot. So respond to the following question with a yes or a no. You give it a couple of examples, and then you ask the actual question. In a few shot setting, you actually see that the bias pattern changes a little bit. You still have some bias, but actually you see that better performing models are also less biased. There's a little bit of clustering over here. So actually, few shot prompting seems to reduce bias. We kind of are guiding the model toward the right direction. And then you can also ask, okay, but what about what can we do about this bias? Can we correct for it? And the answer is we can. So we actually propose a method that, when applied, reduces bias. So here you see crosses where this is the corrected version of the model. And you see that the bias pretty much goes away. And you see that the accuracy tends to go up. Not a lot, right? So like a cool result would be like you correct the bias and then the accuracy is at 1. We don't see that. But we do see a little bit of a boost for a lot of the models. So some masking does seem to be taking place here. And then similar for few shot, where you apply the correction, and here you can see that it is being even more prominent. So models that are already unbiased doesn't matter very much, but models that were biased initially, you actually see a pretty substantial increase in performance once you correct that bias. So what did we do? So now we're going to look at all of the results. We actually had 2 different data sets, COMS and EWOK. You see that the bias actually also differs across data sets, so it's not a consistent bias per model. We tried 2 different bias correction strategies. One did not work, and one worked. The generic bias correction is actually something that's been proposed in the literature before. People are kind of trying to account for just like the base probability of different tokens, in our case yes and no tokens. So here we would just subtract the log probability of the sequence initial yes and sequence initial no from the corresponding log probabilities for yes and no. And it doesn't work. It overcorrects. It doesn't. That actually is not a reliable signal. The specific bias correction approach is data set specific. So we take a bunch of questions in a data set. We take a set of them. We calculate the log probabilities for yes and no, and that serves as our reference point. And so then we subtract that from the held out test of the questions on which we're actually testing. And so this data set specific bias correction actually turns out to be quite effective at almost entirely eliminating the bias. So it's pretty cool. You know, we have a method for correcting bias. It seems to be helping with accuracy to some extent. You know, it's obviously most helpful for smaller models and in zero-shot setting, whereas in few-shot, at least larger models can kind of correct a little bit. So does yes bias in language models arise as a result of statistical learning on language inputs and their instruction tuning? No, language models are often biased, but the bias direction varies depending on the model, the data set, the testing conditions, so we don't see a human-like kind of consistent yes bias behavior. And does this bias mask exist in model knowledge such that correcting for this bias will improve model performance? Yes. Correcting for the bias typically improves model performance. So, you know, why do these models show a bias? Well, they're statistical learners. You know, they are sensitive to all kinds of distributional properties. So it means that the specific data set on which they're being tested will probably affect their overall tendency to say yes versus no, right? So that seems to be a kind of a different mechanism from what humans do. So in humans, those, you know, high-level social factors like the desire to conform, right, they might provide more explanatory power than a simple statistical learning kind of approach. Although, you know, might exist in humans to some extent too as well. And then, you know, this bias correction approach is a way to maybe probe knowledge in language models a little bit better than just simply using log probabilities for yes and no. And then, you know, just a correction, a note that, you know, this method works at the level of log probabilities, as you've seen, so we cannot apply it to ChatGPT. So this is very much, you know, something we can only do with open models from Hugging Face, etc. Okay, so now, briefly, I wanted to summarize by just kind of sharing with you my excitement about the relationship between neuroscience and AI for language and cognition, and just, you know, sharing with you some of the ways I think about the relationship between the two, which, you know, is very much shared with the other speakers in this symposium. So when we talk about the relationship between neuroscience and AI, and here I say neuroscience, but really it's cognitive science and linguistics, disciplines that study the human mind. There are a couple of different ways in which I think that neuroscience and cognitive science can inform AI. So one is conceptual insights. So the formal and functional competence is an example of a conceptual insight from neuroscience that's applicable to AI. Elements of world knowledge. We have a bunch of domains. We have a bunch of concepts that we know are important for humans. We can now go ahead and test them in language models. There are methodological insights. A paper I did not talk about today is this do's and don'ts of experimental design for large language models, which is a little commentary piece that I put out. And, you know, Mike Frank was talking about that as well, where we trained as experimentalists. So, you know, there are just control conditions that might be good to have when you're trying to figure out what these models can and cannot do. But of course, there is also the other direction, and so AI can really help us understand the brain better. One way in which it can is using large language models as computational tools for stimulus design, or of course as encoding models of the brain, as Shaylee talked to you about and Ev talked to you about, and we have some ongoing work in the lab about that as well. And LLMs as model organisms, which is also a way that people have been talking about them in this workshop, where we now have these models that learn statistically on a large corpus of language. They learn a lot, and so you can measure exactly what is learnable. They can serve as existence proofs for all kinds of theories about learning language and learning from the world, and also as a source of hypothesis for what kinds of things might be happening inside the human mind. All right, with that, I would like to thank my co-lead authors, my mentor, Seth Fedorenko, Jacob Andreas, other co-authors, my lab, and all of you for listening.
Questions?
I'm not sure why. Did you say why you think there is a no bias in the models?
Why there's a no bias? No, and it was that data set specific, right? So I showed it to you for EWOK, for comps, it was mostly a yes bias. So it seems like it's just subtle distributional properties of the data that might be influencing the model's response, would be my best bet. But I wouldn't say it's a consistent no bias, it's just like, it just varies. Yeah.
I just have a bigger picture question. Like, one thing that really impresses me about cognitive scientists and linguists is their ability to design very insightful experiments to probe cognition or language and so forth. I'm wondering if there's a way to systematize that or make it algorithmic in a way to probe LLM understanding or knowledge. Like, is anybody thinking about that? Like an algorithmic theory of experimental design to understand LLMs that might operate in a closed loop with them.
Yeah, so EWOK was a lot of work, right? It was a lot of people writing templates by hand. And we would love to automate that process. And I think it's hard. I have a kind of deep-seated suspicion of LLM-generated stimuli because I feel like they might cheat and just generate stimuli that are easier for them, like more aligned with their distribution, which you can kind of try to mitigate by creating stimuli with one model and then testing another. So you can try, but there is just always this caveat. I think it's probably fine. It just needs to be tested systematically. But of course, the intellectual work of designing control conditions, that's something that's not easy to offload. So I think you would need to be very specific when given instructions to a language model to generate a bunch of stimuli according to certain rules. Can you try and ask LLMs to tell you what these rules are? I don't know. It's definitely an area where it feels like a little bit of an art rather than an algorithm that you follow. But I think it's a cool direction to try. If anybody wants to automate EWOK for extending to other domains and new templates, that would help a lot. So I'd be down.
Yeah, one comment along these lines is just as it's possible to try to come up with sentences that, for example, different language models, right, maximally disagree on, as far as the log props, or sentences that people's judgments and models' judgments maximally disagree on. That work, to my knowledge, has mostly focused on more linguistic tasks, but it's possible, in principle, to do this for sort of more world knowledge, right? So what are the things? What do the sentences, what do the prompts that are easy for people and hard for models have in common, right? Because a lot of the existing work, right, focuses on very isolated cases. Here's a little problem that stumps language models, and often in those cases, the authors, it's trivially easy for the authors, but inevitably, people come in responding well, hey, it's hard for a lot of people too, and you didn't consider that, right? So it's a challenging. I appreciate your point about cognitive sciences being good at that, but it's hard for cognitive scientists also to generalize even we've worked with your EWOK data, and it's genuinely hard to draw kind of generalizable conclusions. Okay, what do they really have in common?
Yeah, so we did these analysis, the EWOK analysis, in a hypothesis-driven way, where These are different domains. We also tested a bunch of things. We had templates that we label them direct as indirect in terms of like how much of a logical leap there is between the context and the target. We looked at at the length of the stimuli in words to see whether length is a predictor. We looked at what the contrast is between the targets. So for example, instead of Fatima House's teacher versus Fatima House's student, we can have Fatima House's student versus Jose's Fatima's student, right? So you can flip these instead of contrasting the concepts. So we had a whole bunch of like hypotheses as to what might make it harder or easier, and then we threw them all into a single statistical model because you have to if you want to see how these different factors contribute to the overall performance. And so we're now doing this a little bit better. Instead of direct and indirect, we're now looking at like whether the context entails the target and vice versa. So there is a lot more we can do on the kind of hypothesis-driven front. We are also starting to think about data-driven ways of explaining model performance. There is cool work from others adapting the item response theory from psychology to do kind of like a factor analysis over a model's responses to all kinds of items to pull out the latent factors, right? What latent factors predict whether a model will succeed on a specific task or fail, in a data-driven way, agnostic of what I think as an experimenter, and then interpret those factors. So we're planning to do that with EWOK, which I think will help, because our hypothesis can only go so far.
By the way, the same kind of questions actually arise in system theory, in system identification.
I was about to say.
Not much has been done in nonlinear system identification. Yeah. We're still at the same point that we were maybe 10 or 15 years ago.
Yeah, I was going to say linear system identification is a good example. But
linear systems, we know quite a bit. Nonlinear systems, zero.
Do you think just like making LLMs better, like better training data, better reasoning will eventually solve EWOK fully? Or do we need like actually better grounded models or things like that? I remember, for example, like there's a lot of papers that say like Bender and Collar had these examples are impossible to learn for LLMs. And a few years later, I think many of these examples that are cited in papers are eventually learned, like these examples where you need physical reasoning or grounding. Do you think EWOK will also go that same way that like eventually pure LLMs will get there, or like?
I have a theoretical response and a practical concern. Maybe I'm going to start with the practical, because I think EWOK will be solved because it's going to be leaked and people will fine tune on it, and like so we've actually thought about it quite a lot. It's like we're doing science and we're like, oh, what are these companies going to do? And now they're going to claim that they solve world knowledge. So like we are not releasing the items plainly online as text. You have to like log into Hugging Face or unzip the file that you pull from GitHub in order to prevent accidental leakage. We have like terms of agreement. We're thinking about what kind of license you can have for data sets. The license that we want is essentially if you train or fine tune your model on our data set, you have to tell us, you have to make that information public. And so we're actually talking to lawyers to figure out how to write a license and spread it in the community. So stay tuned on the license side. So yeah, kind of will models solve EWOK? They probably will, and probably for a boring reason. But the theory side of your question is more interesting. And well, what do you call a large language model? Like is RAG a large language model, or is like a large language model plus, right? So again, now we have all kinds of augmentations that are happening, and so what kind of augmentations will help is hard to say. Is it just the data? If the data is now more balanced, if you get rid of the reporter bias, will that help? Probably. But then also, as I was saying in response to Gary, I think the important thing is building consistent internal models of the world. And that's kind of the big challenge, that I think it's still an open question to what extent models can do that, and are they doing that in a human-like way, right? And I think it's like super fascinating, super cool. I'm not going to say it's impossible, A, because I'll be shooting myself in the foot, and 2, because I don't think it's impossible. And so the question is like, how are we going to get there? What architecture, what training data, what learning objective will get us all the way?
Well, there have been efforts in the past to encode world knowledge and create huge databases of that, like this type project, for example. Is there any way you can use this old stuff in training or evaluating language
Yeah, so COMS, Kanishka Misra's data set is based off of ConceptNet, I believe, which is kind of this like, knowledge graph of items and their properties. So this information is definitely there and is definitely useful. But the thing about world knowledge is that it is like vague and brittle and incomplete, and event schemas like rabbit chases a fox. How do you encode that plausibility? It's almost in some sense a similar problem to what language was facing, where just encoding the rules of syntax symbolically doesn't get you all the way. So I wouldn't be surprised if conceptual knowledge is also kind of fuzzy and you can't just rigidly encode it with a graph, but it can, potentially serve as a good starting point or augmentation tool to speed up model learning and training. But yeah, fully symbolic systems, they're hard to do. And I think for factual information, like Wikipedia style, it's easier than for this very basic general world knowledge.
Thinking about what it means to have knowledge. So if it's in a knowledge base, you can just look in there and see if the statement is there. But if you look at one of your kind of systems, I guess we can have knowledge in different forms. So we can ask, in a way, there are different ways of probing the knowledge, and it might be represented in multiple ways and places. So, for example, we could ask, what's more probable, cat chasing the mouse and the mouse chasing the cat? But we could also say, what's the referent to the word it in the following string? Right? The cat saw the mouse, but it got away.
Which is the Winograd schema challenge, which is a common world knowledge data set which is formatted exactly like that people use. Yeah.
Right. So I just bring that up as one example of how you can have two different probes for the same knowledge, right? Mm-hmm. We could do pronoun resolution, and we could do just explicit querying. And in these systems, it's not yet clear how many different ways they represent the same knowledge, or what it actually means to have a local representation of that knowledge. And your experiments and others kind of do what we can do, which is we probe the overall behavior of the system without really looking, if I understand, you didn't really look inside to see
Not yet.
where it is. So, sorry, this is kind of I'm not sure what my question is, but it's something like, if we're interested in whether a system has the knowledge, is this so different from formal proof systems where there's an axiom and you could say, yeah, it's there or it's not. And here it's all embedded in some global collection of parameters that we need to refine our question to ask, does it have knowledge useful for this purpose versus that?
Yeah, I think you're raising a really interesting point, right? So by default, we have this idea, okay, you have your internal knowledge base, there's this knowledge of a concept, and then you can access it in different kinds of contexts, right? And so when we were thinking in EWOK, how do you tackle the knowledge of a concept, is through the use of that knowledge in a specific context, in a specific example, right? So we are probing knowledge through the use of that knowledge in order to make, appropriate next word predictions or answer a question and stuff like that. And I think you're right that kind of the more evidence we have of successful concept use in different contexts with different tasks, the more robust our belief then is that, oh yeah, that knowledge is there. Your point though about kind of internal representation also stands, because it might be that for pronoun resolution you use the concept of cat or whatever over here, and then for EWOK you use the concept of cat like in a different part of the network, right? It might, like the multiple random representations might be there. And yeah, so I actually think that EWOK is a really good candidate for doing interpretability work, to look inside the language models to see where these concepts are represented. So I'm, still looking for a lead for that project, but hopefully it's going to happen. And I think the questions you're raising are exactly the kinds of questions we should be asking. What does it mean to know? You know, can we probe the usage of a concept in multiple different ways, and do these ways all load onto the same representation inside the system or separate representations? I think these are all amazing questions.
Let's thank 3:30 we have Boaz Barak for a change of flavor on solving adversarial issues with scaling up system.